Hello, I'm Matthew Sarnowski, and this is Team 5's Project 3 presentation. The overall goal of our project is to aid farmers in maintaining their crops and keeping crops healthy throughout the growing process. The overall objective of our project focuses specifically on fertilizer use and the fertilization of crops through a smart system to automate the process, making it easier on farmers to monitor and maintain crop fields. With this in mind, we chose to work towards the sub-problem of using image processing to determine crop health. Our group met 10 times throughout the course of Project 3. For each meeting, there was a team leader assigned to direct the meeting, keep the rest of the group focused, and keep our conversation on track. We also assigned a devil's advocate for each group meeting. This member served as a way to check and make sure each decision we made towards completing this project was logical by having a controversial opinion to what the group was discussing. This allowed us to be more confident about each decision we made. When there was a disagreement during one of our meetings, the team leader for that meeting would initiate a discussion to hear out both sides and help the group come to a consensus. Our engineering specifications were determined based on what we thought a farmer would want in a product and what would aid them most. These specifications were agreed upon by each member through heavy discussion, driven by how much our product would benefit from the requirement. Our devil's advocate was crucial in this process. Here's our Gantt chart we followed throughout the course of this project. The names listed in the Assigned To column are the leaders of the task. Each group member still contributed, but the members listed took on leadership roles. This included keeping the team on task, checking the quality of the work done, and making sure the task is completed on time. This way, work was divided evenly, and each group member had a fair opportunity to contribute.
As part of our research, we reviewed studies conducted at multiple European universities. We read a study conducted at Aalto University in Finland to learn more about soil sampling, and a study conducted at the University of Antwerp in Belgium to learn more about the use of drones in agriculture. We also used various other sources, such as the European Journal of Remote Sensing, in order to learn more about the analysis of crop fields using thermal imagery, as well as the Food and Agriculture Organization of the United Nations, where we learned that over 200 million tons of fertilizer is used worldwide. Lastly, we looked at the website of the company Botlink, a company which specializes in drone software, to learn about the use of RGB cameras to measure crop health. Here is a representation of our system, which includes many tasks that take place on a farm. The highlighted system shows the subsystem which we will focus on. This is our work breakdown structure. Our design will focus on the analysis of data from the drone. According to our engineering specifications, we will need to supplement the consumer needs of accuracy, speed, ease of maintenance, and consistency. Thus, we will need accurate test readings, fast data analysis, easy to change parts, and a consistent light level during the day. For our calculations, we used VARI indexing and TGI indexing. Both of these indexes are used to measure crop health based on the ratio of red, green, and blue color values in each pixel of the image.
So for our design philosophy, I'm first going to take you through the ideas that we implemented. You can see a picture of our prototype on the right, and there is an RGB camera that is used to take a picture of a test image, and that's right here at the bottom of the picture. That's actually the front of the prototype, and we just set up the test image across from the camera so that it can take a picture of it and sends it to the Raspberry Pi Cricket that you can see inside the box, so that Raspberry Pi Cricket does the image processing and puts it through the TGI filter that James explained. So we made decisions for this design through discussion and testing, and as you can see here, I just wrote down some of the rejected ideas that we ended up not using even though we discussed, such as using a phone camera. We decided that using the Raspberry Pi camera module to keep everything integrated would be better. And another one that I didn't write down was that we decided to use the Raspberry Pi instead of the microbit because the Raspberry Pi provided more functionality for image processing. So one of the one of these design changes that came very late in the design process was actually using TGI index instead of the VARI index. And that came about just because the VRI index wasn't performing as we expected it to, and we knew from our research that the TGI index could produce similar results, and the VRI wasn't exactly working in our software. So for our software design, we started by researching existing examples of code for the Raspberry Pi, specifically how to use the camera module for the Raspberry Pi, and we used that to learn how to take pictures and save the images from the camera. We also had to learn how to use the Pillow or PIL module to read JPEG images, because that's the image type that the camera for the Raspberry Pi uses. And then other than that, we just used similar image processing techniques from Project 2, but with TGI index formulas instead of edge detection. Our prototype had both positive and negative aspects on both ends of the spectrum. Most of our positive attributes stemmed from the fulfillment of the engineering specifications that we outlined earlier in this presentation. So our prototype was able to make consistent TGI readings between tests, and this was due to the consistent level of lighting in the tech fair room that the camera was in. So this meant that there was no visible difference between two tests of the same image. This means that our system was well designed in that respect. Our system also met speed goals. In the engineering specifications, we said that it should take no more than 2 to 3 minutes to run, and it actually took less than 1 minute to run a full test. This means that we actually exceeded expectations in that part. We also exceeded expectations in making our system easy to maintain, because in our engineering specifications, we said that it should take no more than 5 to 10 minutes to take apart any single part of a prototype, but it actually took less than 2 minutes to disassemble the whole prototype, meaning that our system was very easy to use and simple. Our simple design helped us to achieve that. And one other positive attribute was that it had accurate readings, like precise readings. And this precision can be quantified by looking at the visible difference between the brightest and the smallest TGI value in the output image. Because if there's no visible difference, if everything looks the same, it's not going to be very helpful to the farmer trying to use this to decide where to fertilize. The negative aspects of our prototype mostly stemmed from the simple design that made our prototype easy to maintain. For example, our design was very primitive and only ran on sample test images that we printed out on pieces of paper. This is not very practical in real life when you have to, instead of using test images, you have to actually go out and take pictures of real crops, which we were not able to do. In addition, we only used an RGB camera, and we didn't have any thermal or infrared or multispectral readings that would provide more accurate information and give us access to better indices to measure crop health. So this was just a limitation of the resources available to us. In addition, our design was pretty fragile and not very robust. You can't take out our prototype to be used in the field every day for years on end, because in reality, cardboard and tape aren't very robust materials, but they were the best available to us, so this is again a limitation of the resources available. Our final negative attribute of our design that we all agreed upon was that it wasn't very aesthetically pleasing, it just got the job done. So next I'm going to take you through the code that we wrote, and first we just imported our modules that we needed, and I put in comments to explain what each module was used for. So we started the camera, and then we saved the image to that directory, and then we used the Pillow module to convert it to JPEG to PNG so that we can use matplotlib functions on it. So then we used this matplotlib function on this imread to open up this matrix to create this array based on the image matrix, and then we created this TGI array that would be our final output using numpy's zeros function. And we used the double for loop that we've seen before in Project 2 to iterate through the image and perform the TGI calculation based on this TGI formula that we looked at earlier in the research. And then we used matplotlib's imsave to save the final image. And now I'm going to take you through some of the test cases that we used. This is what our first test image, and the first thing our program does is create a JPEG image, a PNG image based on the JPEG, sorry. It just looks exactly the same. And then this is our TGI value for that. It's just a heat map. And this lighter color here corresponds to this more greenish area of the field as compared to this darker area that kind of looks less healthy that shows up as darker on the map, on the heat map. Our next image here has a very visible difference between these two sections of the field on the left and the right, and this difference shows up in our image as darker versus brighter, which a farmer would know to focus on which areas need more fertilization. The same thing can be seen in this test image. You can see that the actual crop part of the field shows up very differently from the non-crops, from the non-field part of the image. And then this image, once again, has like a very green area on top, a road, and then a kind of yellowish greenish area here, and then very brown on the bottom. And you can see in our output TGI heat map that the very healthy parts of the field, this green up here, showed up very brightly, and on here as well, but then the not grass part showed up very darkly, and a farmer would know how to use this information to help decide where to fertilize. So one final limitation of our system, negative attribute, is that the test images that we used were all found online and not taken at the same parts of the day. Like this image is definitely darker than this image, which is definitely brighter than, say, this image. So they all had inconsistent light levels, which can mess with the readings. If these all were to, say, come from the same field, then we would want to take the images ourselves to ensure that the images are taken at the same time of day to ensure that the light level is consistent.
For the conclusion and areas of improvement of our system, our current system implies that the crops are only unhealthy due to a lack of nutrients in the soil, but realistically there could be other factors such as lack of water. So a future model of our system would include the weather data from the last month of the area to see if the area has been in a drought or not, and this would make a more accurate representation of what we need to apply to the crops to help make them more healthy. Another improvement that can be made to our current system is an addition of a user interface that would include choices between which crops are being measured and the date that they were planted. This would help make a more accurate representation of what colors we are looking for in our imaging, and would therefore make a more accurate representation of the heat map for our crop health. Lastly, another improvement to the system would be instead of using the RGB camera that we are currently using, we would use a near-infrared thermal imaging system, which would make the system more accurate when detecting the crop health compared to an RGB imaging system. The physical system is functional, it is not product worthy, so one thing that we would change about that is making it more appealing to the consumer's eye instead of just being functional.